Alright, this is going to be a short video, I suppose. We're going to talk about vertical motion with drag and terminal velocity. And so we did some of this in class. So start with the case where you have an object that is falling and you have the force of gravity acting on it. I'm assuming G is positive. And if the object is falling, so the motion is going to be in this direction, the velocity is going to be in this direction. If the drag, say, is proportional to the speed, then the drag or the force that the air resistance will be exerting on it is going to be in the vertical direction and upward, where this force is going to be proportionally constant k, whatever that may be, and then the absolute value of v, which in this case our vector is just one-dimensional, so plus minus is the only direction that we have. Now, the velocity being negative here, then the absolute value of the velocity, to make it positive, you have to turn it into negative kv. Alternatively, if the motion is upward, if you have an object that is moving upward, where the velocity is positive, well, the gravity is still pointing down. However, now the drag is also going to be pointing down. Now the velocity is positive, but this is pointing down, so we have to make it negative by putting a negative kv. Either way, the sum of the forces is going to be equal to negative mg minus kv. But that sum of forces is equal to mass times acceleration, so that should be equal to mass times the change of v with respect to time. So my differential equation that will govern this whole process is going to simply be dv dt is going to be equal to negative g minus k over m. I divided by m on both sides of the equation times v. And this is a separable equation. It's linear, but it's separable as well. So the way to solve it would just be to integrate dv over, let's leave the negative, let's leave it behind there, g plus k over m, v, and is equal to negative dt. When we integrate on both sides, we have to do a u substitution, where u is going to be g plus k over m. So the u is going to be, our m over k du is going to be equal to dv, and here I just get negative t plus c. I'm skipping step just because we did this in class, so if you were not in my class, you're don't attend my university, I suppose. So we multiply both sides, and we get natural log of u integrating multiplied by k over m. With all the steps I'm skipping, you probably are thinking you're fortunate to not be there. In class, I don't skip as many, I don't think. So then I can exponentiate both sides to get that u is going to be equal to another constant, negative kt over m. And now I substitute in what u was, which I said was going to be that. So I get g plus k over m v equals c e to negative kt over m. And I can solve for v by subtracting g on both sides and then multiplying by m over k. So I'm going to get m negative g over k, plus I'm going to absorb that product into the c. Please pause the video and subtract the g, multiply and divide by k to convince yourself that everything is okay. Alright, so that's going to give me that the velocity as a function of time, and notice that as time goes to infinity, this expression goes down to, am I fitting here still? Already, I think. That goes to 0, so my terminal velocity will be given by this term, negative mg over k. So terminal velocity, if you want to call it vt, I don't know. It's going to be negative mg over k. Now, for the exam, I'll give you the numbers. I do want you to solve it, and do not just give me this formula and give me the terminal velocity. But let's go ahead and put numbers to this and see how it goes. So let me erase real quick, and then we'll be right back. All right, let's use this part because then we have the solution and the differential equation in view. Let's work in the international system. I see that you guys don't like the imperial system. You know my opinion. So gravity will be 32. Wait, I'm insisting on doing the imperial system. 9.8, which I in class turned it into a 10. You see, it's better to use the imperial 32 or make this one a 10. Okay, 9.8 and meters per second squared or per second. And let's say that we have a force or that air resistance is proportional to the speed, and it's given by, say, since it is going to be a force, I'll have to do it in newtons per. So let's say that it is this number is completely arbitrary. So 3 newtons per feet per second. So you could do newton second per feet. How about that? That's better. There you go. And what else? We need the mass of the object, I suppose. And so the mass, let's say that it is an object that weighs 1 kilogram. So we have a stone that weighs 1 kilogram. Then we have the gravity and then the resisting force of 3 newtons times second per feet, or 3 newtons per feet per second, if you will. And now I'm going to say that the object is starting, is going to be dropped from a certain height at an initial velocity of 0. So we're just going to drop the mic. And 1 kilogram mic, that'd be pretty heavy. And so once you solve this differential equation, you will think that this velocity is going to be given in terms of this equation, which is going to be mass, which is going to be 1 times 9.8 divided by 3. And all this should be now in per feet. I said international system, dude. Meter. There you go. Sorry. So this all should be in meter per second in the end. And then this right here will be plus c e to negative k t. K in this case is 3 over mass of 1 t. Okay, so that's what we get. And the only thing we need to do now is to find the constant c. So at times equals 0, we get 9.8 over 3. Maybe we should change the gravity to 9.9, then we get a 3.3 out of this. Somebody doesn't like to do any kind of numbers. And then plus c, as t is 0, this is just 1. That's going to be equal to 0. And then c is the negative of that quantity. So from that, we get our velocity. And I want to do something that you're not supposed to do. I'm going to erase this one here because I don't have room. And I'm going to factor 1 minus this. And I'll get my equation for the velocity. And then as t goes to infinity, good, that was squeaky. As t goes to infinity, this term disappears and my terminal velocity should be, where did my negative go? At least I'm consistent because I did it. I made it here negative, so that makes it into positive. So I can put a negative here, and then everything is alright. There's a negative. I didn't see it. So the terminal velocity, of course, now that when I went ahead and looked at terminal velocity, it has to be negative, right? Because you're gonna drop the object, and it's gonna reach a terminal velocity that's very negative. So it's gonna be, if this were positive, we'd have a problem. Physically, it wouldn't make any sense. So it starts resisting and suddenly the thing levitates and goes up into this. Never mind. At that point, we'll compute the escape velocity of that object, which we did in class today. Anyways, too much talk. This is what you need to know for the exam. So I'll leave it there. I'll wrap it up. I'll see you guys in the next one. Thank you for watching, and good luck in the exam.